Okay, so now we have time dilation, length contraction. We want to start thinking about what it means to change reference frames or transform from reference frames. So a while ago, we saw the Galilean transformations when you're thinking about the position of something or its velocity in one reference frame versus another reference frame that's moving relative to that first one. Let's just jump back real quick. These are our Galilean transformations. Pretty straightforward, intuitive. Now we want to see what happens when we take relativity into account and time intervals and lengths do not remain constant. Just to note here, we're going to get from positions and time transformations, but eventually we're also going to talk about velocity transformations, and we end up talking about kind of different velocities. One, when we say v, or write down v, this is usually meaning the velocity of one reference frame relative to the other one. So since we already use v, when we're talking about the velocity of objects in those reference frames, we're going to use u. And then just one other thing to note here, in Galilean transformations, the time measurement is the same in both reference frames. This is going to be a very large change now into relativity when we're going to get these Lorentzian transformations. The fact that the time is the same in both these reference frames also means that there's no change for velocity, right? Because the velocity is just the derivative of x with respect to time, the derivative of position with respect to time, and the accelerations are exactly the same in both these frames because that's the second derivative of position with respect to time. Okay, so let's go ahead and try to relate the positions in these two different reference frames. So like the position of this event that happens in these two different reference frames. So in the x reference frame, that event took place at x. We could also say it is that distance vt, the velocity and the time elapsed for the second moving frame. It's that vt distance, plus the distance from the origin of this second reference frame to the event. Right? In the prime reference frame, that's just x prime. That's the distance measured in that moving frame. But we're talking about the unprimed frame, this stationary frame relative to that. So what's added here is the distance between the origin of that moving frame and the event, which would be x prime, but that is in that reference frame, meaning that x prime is actually the proper length that you would measure in the prime frame. So if x is the proper length in the prime frame, then the length that we see in the unprimed frame, in the stationary frame, is this contracted length, 1 over gamma times x prime. So this is a relation, but it's a mix sort of these prime and unprimed frames. We want to get rid of that, where we'd like them just to be primed or unprimed on either side. Let's go ahead and subtract that vt and just flipping this around. Okay. Now we have a measurement in the prime frame and the moving frame in terms of all unprimed things, right? X and t. We could have done the exact same thing from the x prime frame. The relative velocity is the same. It's just that now the unprimed frame will be moving in the opposite direction, meaning that the same logic works except for the velocity is in the opposite direction. This is going to end up being almost the same equation. It's just that for the unprimed relative to the prime ones, it's actually plus here. All right, that's all well and good. So now we have our transformations for position, for x. What about for time? Time is a bit more involved, but we're basically taking this relation and plugging it into the prime frame here. I guess maybe I'll just keep those gammas outside for now. Oh, that was why. There are two gammas here. And yeah, so this is x going into now the x prime. We're replacing x in the prime transformation here. Just dividing by gamma, get to there. So we want to get all the unprimed stuff on one side, prime stuff on the other side, so Vt, subtract that x prime over gamma. And now I want to combine this into one fraction, meaning that I need to force this common denominator. So basically I'm multiplying this first term by gamma over gamma. So now I can actually combine these are like terms. You can also distribute this gamma squared. It's all over gamma now. Oops. So now we got some like terms in the numerator. I'm going to go ahead and combine those and factor the x prime out. Gamma squared minus 1 plus gamma squared t prime. That was all over gamma. And remember, this was equal to Vt. We're going to actually move that V over now, just like that. Okay, and at this point, you can do this as your own algebraic exercise if you want. The gamma squared minus 1 can actually be written as b squared over c squared minus v squared. And that t, now we can write as x prime, and just replacing this gamma squared minus 1, b squared over c squared minus v squared, plus b gamma squared, or keep writing the same way, gamma squared b t prime over b gamma. And now we see in both of these terms there's at least one factor of the relative velocity of the frames, this v. So we're going to get rid of that, and one of those. Finally, we're looking at v x prime, c squared minus v squared, plus that gamma squared t prime, that's still all over gamma. Let's keep going. One more aside here. It turns out that this 1 over c squared minus v squared, we could also then kind of revert and rewrite it as gamma squared over c squared, meaning now that t is going to look like, what is that, gamma squared b x prime over c squared, using that to replace the c squared minus v squared. And now we have gammas all over the place. We can cancel some of them out. Gammas in both of these can factor it out. And there we go. That's sort of your final result for the relationship between the measurement in the unprimed frame and the time measurement in the prime frame, in the moving reference frame. And here you go. So I just showed you at least the transformations for time, the t-coordinate, transformations for x coordinate. Y and z actually are unaffected because the motion is all in the x direction. So you can write them in terms of v squared over c squared, or kind of combine some of that stuff and write them in terms of the Lorentz factor. There you go. These are what's known as Lorentz transformations, or the Lorentzian transformations. This is the equivalent of the Galilean transformations. But now we're talking about relativity. things moving very fast. So even though the y and z coordinates are unaffected here, we're going to look at the velocity transformations in a minute, and it turns out that the y and the z velocities could be affected because, right, the velocity is a change in position over a change in time. Since the time measurements are different in these different reference frames, that means that these y and z velocities are going to be affected. All right, another example about that. It's actually going back to the earlier setup where there's an observer watching a train zoom by and some light flashes. So now we're going to put some numbers to that situation because we can now transform between these two reference frames. So we got an observer shown standing by the railroad tracks, sees these two light bulb flashes simultaneously. So they're going to see the light at the same time. At both ends of a 26-meter long passenger car, when the middle of the car passes him at half the speed of light. So find the separation in time between when the bulb flashes as seen by the train passenger who's seated right in the middle of the train. Okay, so the time interval in the stationary frame, right, the person standing on the earth watching the train zoom by, that time interval is 0. There's simultaneous events. The relative velocity of these frames is v, which they tell us is half the speed of light. And the distance that we're talking about, the difference from the front to the back of the train, is measured in the frame of the train, in the reference frame of the train. Normally you'd measure the length of a train, you stand next to a train, this is this distance, right? I'm at rest with respect to the train. But that's now the distance in this moving reference frame. So this measurement is actually the primed frame. So then if we go to our Lorentz transformation here, just talking about differences instead of, to single coordinates. Then, right, this was 0 in the stationary frame. Meaning I just divide by that gamma, and then we actually want, right, the time interval that the person on the train would measure. Missing a squared? No, missing a squared. That should have been squared. It's just going to be that. So they tell us the velocity is half the speed of light. The distance in the prime frame was 26 meters. 6 squared. So that's where it's going to go away. And this is, I don't know how much right here, but the units for the speed of light are meters per second, just like any speed, so we're actually going to get units of time in the end of seconds, which is great, because we're talking about time interval. And that turns out to be minus 4.33 times 10 to the minus 8, right? Very short time interval, even though the train is moving at half the speed of light, the distance between these events is very short compared, when you're thinking about light traveling. 26 meters, not very far. And it's negative, meaning that the person is actually seeing the front of the train flash before the back of the train. Now that we have these transformations and we see this sort of interplay of space and time and how they affect each other, well, we essentially come to this concept of space-time, as opposed to classical physics where space and time are these separate things. Time is absolute. In fact, in classical physics, it's just a thing that takes away. In relativity, space and time are now interconnected, and depending on how you're moving through space, it affects how you perceive time, or the time intervals that you would measure. Putting these two ideas together partly comes down to thinking about what it means to measure displacements in space-time. So if we think about measuring displacements in space, in regular space, without relativity, this is how we would measure a displacement between x1, y1, z1, x2, y2, z2. That's a displacement measurement between them, that delta r squared. And it turns out that that measurement of displacement is what we call invariant. It doesn't change depending on what reference frame you're looking at it. You could rotate around, right? You can translate it. That delta r squared is going to remain the same. It's invariant. However, this is not invariant when we're talking about relativity, right? Because space and time are interconnected. When you want to measure displacements now in space-time, we need this delta s squared thing. So it's the same, except for we now have to add, or technically subtract, this term having to do with time, c delta t squared. So this is displacements. If we talk about then thinking about infinitesimals, we go those displacements going towards 0. This is the infinitesimal version of this displacement measurement in space-time. This, it turns out, is an invariant when you transform between reference frames, relative reference frames. It's a very nice thing to have, is a measurement of displacements that doesn't change depending on your frame of reference. So we're not going to go too much into the depths of space-time. It's fairly beyond this chapter and beyond the course, but just to say that you can think of space-time essentially just compress all of the spatial axes to one direction. You have space and you have time. And an outcome of this displacement that remains constant is that you have, well, these two kind of opposite ends of the spectrum where that measurement is greater than 0, meaning that the spatial portion of it is larger than the temporal portion, so we call that a space-like separation. That's like the measurement from A to C in our space-time diagram. So being space-like, A and C are points where light can't even travel between them, right? They're only connected in the sort of spatial way. The other end of that is when the spatial portion of this invariant is smaller than the temporal portion. We get that the delta s squared is less than 0. This is what we call a time-like separation or time-like displacement. And these events like A and B are ones that light could travel between. It's not really clear maybe right now, but the fact that light can or cannot travel between events essentially means that those events can or cannot be causally linked. So in a space-like event, if even light can't travel between them, then there's no way that they could be causally connected. Versus the time-like events, light could travel between them, so there is a way that they could be causally connected. And it's very difficult to think about this at first, but we're talking about a displacement in space-time. So if you're thinking, oh, well, light could travel between any two places at once, it just takes some amount of time, but time is incorporated into our picture now, right? So A and C are not just difference in spaces, these are actually particular times of these events too. So that's why A and C are, say, things that happen, but light can't even travel between them. And then right in the middle, when the spatial portion, x, y, and z, are equal to the temporal portion, that is what you might call a light-like displacement. And that's actually what defines this cone. We call the light cone. So any events inside of that light cone from A are events that could be causally linked to the event A. Events outside of that light cone, like C, could not be causally linked. So in a sense, that light cone is sort of like a barrier of causality. Like I promised earlier, we're now going to get into what happens to velocities in different reference frames. We can do this fairly simply. It just takes playing a little bit loose with math. And as I mentioned in the class meeting and maybe in lectures before, there's sort of what you might call physics math, which is, I don't necessarily understand all the details, and maybe a mathematician would tell me that I'm missing all kinds of steps, but it works. So we're going to do it this way. Right. So from our Lorentz transformations, we had this for a relation between position in the stationary frame or the unprimed frame relative to the position in the moving frame, prime frame. And you can sort of think about this as we want to get to a velocity, so we want to talk about a differential of x in terms of differential in time, or dx and dt. So kind of think about this as like what you do when you when you use a u substitution in calculus, right? You say u is equal to something, and then you look at the differential of du is equal to is that thing. In this case, it's going to turn out to be, it's pretty straightforward. there's actually two variables here, but they're not connected within the prime frame, so we're fine. There's different differentials. Similarly, for the time transformation, if we look at this sort of differential form, look at that. And now we're going to do a very probably vexing thing to mathematicians, and we're just going to divide these two things to get, well, those are going to go away. To get that. And then we're, essentially this is now the velocity in the unprimed frame, in the stationary frame. I want to relate it to the velocity in the moving frame. So I'm going to do some more bad math here and multiply by this 1 over dt prime over 1 over dt prime. What's that going to get us? Well, it looks like it gets us that. So that's the velocity in the unprimed frame. Now we have dx prime dt prime, that's the velocity in the prime frame. dt prime is just 1. That's just 1. That's the velocity in the prime frame. So that's the velocity in the x direction when you have these relative frames moving along the x-axis. There's some of the other ones for y and z, in the velocity in the y and z direction. And like I said earlier, because the time coordinate is actually affected by the motion in the x direction, and the velocity is dependent on the time, then we actually get a change in the, or an effect for the relative velocities in the y and the z direction, even though there's no relative motion in those directions. So just checking on our sort of continuity idea that we're going to get back to our whole understanding, our normal understanding of how velocities transform when we're not close to the speed of light. If we look at our x velocity, when v, the relative velocity of these reference frames, when that is much less than the speed of light, that v u prime x over c squared is going to go to 0, meaning the denominator is going to 1, meaning we're getting back ux prime plus v. We get back to the Galilean transformations. All right, let's take a look at another example. What happens if you're in a spaceship, you're traveling very, very fast, half the speed of light, and you shoot a laser in the direction you're traveling? We'll think back to Galilean transformations. The velocities are just going to add. So the speed of the laser is c, the speed of the ship is half c. So normally we think that the speed of the laser that somebody, say on Earth, is going to see is going to be c plus half c. It's going to be 1.5 c. That's no good though. So the velocity the person on the Earth is going to see, this is in a frame stationary relative to the velocity of the light in the spacecraft reference frame, related to the velocity of the spacecraft, right? That's the relative velocity of the person in the spacecraft here. So the velocity of the light in the spacecraft frame is c. That relative velocity is 5c, meaning we're going to get c plus 0.5 c over 1 plus c squared. So those c's are all gone. So it's then get 1.5 c in the top, but we also have 1.5 in the bottom. C. There you go. The speed of light is still the speed of light, regardless of the reference frame that you're watching from. Okay, so that last example was good. It kind of just reaffirmed the second postulate that speed of light in a vacuum can be measured to be the same regardless of what reference frame you're in. How about, we're not talking about light, we're talking about an actual massive object that gets shot out from this spacecraft. So we're still thinking about the spacecraft going along at half the speed of light, and now it's shooting out this object in its reference frame. That speed of that object that it shot out is 0.75 the speed of light, 75% the speed of light. So what is the velocity that an observer on the Earth would say that projectile is coming out? Let's just write some of this down. This is the relative velocity of the reference frames. You could write ux, but there's only one direction of the speed. We're just going to write it as u. The velocity of the projectile in the spacecraft's frame, then the velocity that the person on Earth would measure from our transformation, velocity transformation. It's that. So 0.5 c plus 0.75 c when all the velocities are given relative to the speed of light, all this stuff usually works out pretty nicely. And this looks like 1.25 c over 1.375, which turns out to be about 0.909 c, right? Or about 91% the speed of light. So even though this projectile was shot at 3/4 of the speed of light from an object moving half the speed of light, it still only got to about 90% the speed of light. This is very different from the Galilean transformation. And just to note too, that this change in velocity that the person on the Earth saw, it changed by what, about 15%. So that was A. In B, we're saying, okay, well, what if that projectile was actually shot backwards, away from the, well, in the opposite direction that the reference frame was going? It's going to look all the same as this, except for, this is negative, that's negative. I could write it off. Well, the end result is that we get 0.4 c minus 0.4 c. That is the velocity in the moving reference frame. The velocity that the observer on Earth actually ends up seeing is minus 0.4 c. This now, what is that, 25% change? So there's a big difference in the change or the velocities that you're seeing, if it's going at you, going away from you. Very strange stuff. But again, these are not normal situations. We're talking about rocket ships moving at half the speed of light. Like, that's something we can't accomplish right now, but we can theorize about and then make predictions about things that we can measure, and all those things confirm that this is how it is.